Great. Without further ado, I'd love to introduce our next speaker. Our next speaker is a pioneer in both machine learning and online education, and it is not an exaggeration to say that he has changed countless lives through his work in machine learning. Previously, he served as the chief scientist at Baidu, the founding lead at the Google Brain team, and the co founder of Coursera, the world's largest MOOC platform. I would love to welcome the chairman and co-founder of Coursera, adjunct professor at Stanford University, founder of Deep Learning AI, founder and CEO of Landing, managing general partner at AI Fund. I don't know how he does it all, Andrew Ng.
Hey, thanks, Artie. It's good to see you. Had the pleasure working with Artie way back at Stanford and a few other places. It's nice to see you, all of you here today at this Snorkel event. You know, I've had the deepest respect for Chris Ray and Alex Ratner's work for many years. Alex had the privilege of hosting Alex at the Deep Learning AI event like a couple months ago, and I'm now really glad to be speaking with all of you here at this event as well. As Artie mentioned, I think this new UI is great. Would love to hear your comments. Type at me, criticize what I'm saying, and ask questions in the Q&A as well. What I hope to do today is share with you some tips on a data-centric approach to AI. So I know we've been hearing talks all day about data-centric approach to AI, but let me just tell you what I mean and some of the things I saw with the rise of data-centric AI. For many years, decades, the conventional approach to AI was AI systems need code plus data, and many people, including me, would download some data sets and work on the code. It was actually thanks to this paradigm of development that I think today, for a lot of applications, the code is basically a solved problem. That open sourcing you download from GitHub basically works well enough. And instead, it's more useful to find tools and processes and principles to systematically engineer the data to make the AI system work. And I know many people have been talking about this. And I think for many applications, like computer vision, until as recently as 3 or 4 years ago, I think the code wasn't good enough. So in some domains, not all, I think the rise of data-centric AI is actually now's the appropriate time. Whereas in computer vision and speech, I think we frankly weren't ready, say 5 or 6 or 7 years ago. But it does vary by domain. So I started to talk about data-centric AI. So Landing AI has been working on data-centric AI for a couple of years, building the data-centric MLOps platform for computer vision. I started talking about this in a YouTube video on March 23rd or March 24th. You can still find that YouTube video on YouTube. And I was actually really excited that since the words data-centric AI weren't actually kind of on the internet in this present form at that time. And I was actually really excited that since that presentation, many great companies have started talking about data-centric AI right there on their homepage. Curly Technology raised a bunch of capital to build data-centric AI. I was excited that Scale AI wrote data-centric, right there on the homepage. And of course, deepest respect for really what the whole Snorkel team is doing. But I was actually really excited when, even Snorkel started using the words data-centric AI on their homepage. Um, so with the evolution of a new technology approach, this is the process that we as a community, typically go through, right? And so often there starts to be a handful of experts that do something intuitively. In fact, with the rise of deep learning 10, 15 years ago, what I saw was, 15 years ago, there was a bunch of people hacking up neural networks in C++. It was very manual, very error prone, a few people could get to work. And then eventually, thanks to meetings, maybe like this one and other meetings, the principles become more widespread. And then there were hundreds of people, maybe thousands of people hacking up neural networks in C++. And it kind of worked, but was still error prone. And eventually there arose tools like TensorFlow to make the application of this new set of principles and ideas more systematic. So I think that we've actually been in this phase for quite a long time, many years, in the case of data-centric AI, where I think when I was building a speech system many years ago, I would just ask my team to collect more data. But frankly, even I didn't quite know what I was doing. I was kind of doing it intuitively, and many others around the world, applied machine learning practitioners. I think that we are now firmly in this phase of the principles becoming more widespread and more people having this mindset and being able to apply a systematic way of thinking about entering data. And I think we're in the very early phases with companies like Landing AI, Snorkel, and many others working to create tools that hopefully will enable many people to apply these ideas in a more systematic way. Now, what I thought might be most useful today was I'm going to share with you my top 5 tips for data-centric AI development so that after this presentation, you can all go and, if you wish, apply these tips. The tips I'm giving are a little bit more applicable to unstructured data, so images, audio, where you can get humans to label the data more easily and where data augmentation may be a little bit easier. But some of these ideas also apply to structured data or to tabular data. But so I'm going to run through these 5. Feel free to screenshot this if you want and save this for your friends. Right? Make the list consistent. Use consensus labeling, spot inconsistency, clarify label instructions, toss out noisy examples, use error analysis, focus on subset of data, and improve. So let me dive into these one at a time. Tip 1, make the labels wide consistent. So the best thing for a learning algorithm, or at least it's much easier for a learning algorithm to learn a problem if there is some deterministic, meaning non-random function mapping from the inputs X to the outputs Y, and labels are consistent with this function. If you can engineer a data set to be like this, you can often get things to work with higher accuracy and or a smaller data set. So I've been doing a lot of work at Landing AI on manufacturing visual defect inspection. And if you're trying to help biopharma inspect pills, so pharma, right, makes a lot of pills, and you want to find defects, like scratches on these. If you have labelers label the pills like these, defect, okay, maybe you have a data set like this. Well, it turns out that if you were to plot stretch length against whether or not there's a defect, this data set, at least plotted this way, looks pretty inconsistent. And you actually see this all the time. Even human expert inspectors or human expert radiologists or human expert whatever, they've done this for years, they will often disagree with each other. And if you're able to spot this problem, how to spot this problem is something I'll touch on later, and sort all the images in order of increasing stretch length and relabel the images so that the ones below, say 2.5 millimeters or whatever, are not a scratch, are not a defect, and things larger than that are defective. So you can ignore the tiny little defects, but the big scratches, boy, that's a defect. If you're able to make the data consistent like this, it turns out to be much easier for the learning algorithm to learn to make accurate predictions. It turns out, I know there's some of you in the audience are very technical. So it's a little bit technical. If M is a training set size, there's a theory from pack learning, realizable versus agnostic learning. But it turns out that if the data set is noisy, if there's no deterministic function mapping for X to Y, your error decreases as order 1 over root M, where M is a training set size. But in some cases, you can prove that if there is a deterministic function mapping from X to Y, your error decreases like order 1 over root 1 over M, and 1 over M as a curve just decreases much faster as a function of M. So your error decreases much faster. Or in other words, you lower error or you need a smaller data set size in some cases. Tip 2, use multiple labelers to spot inconsistencies. So if you suspect that labelers are inconsistent in how they're annotating the data, I will often trigger asking 2 labels or sometimes more to label the same example. So if labeler 1 labels as a chip, labeler 2 labels as a scratch, well, that's one inconsistency. And what I want to do is just step through a view some of the most common inconsistencies I've seen in computer vision, but very similar things apply to other forms of unstructured data. So label names, common inconsistency, or bounding box size. So label 1 says that's this color, label 2 says that's this color. See, this is very common. Or label 3, or third example, number of bounding boxes. 1 labeler draws a bounding box around the chips. Label 2 draws 2 bounding boxes. So I've actually seen all of these in many computer vision contexts, and being able to clean this up significantly improves the learning algorithm performance. And in terms of the iterative workflow of developing machine learning system, when I'm building, computer vision system or other systems, I often will repeatedly clarify labeling instructions by tracking down ambiguous examples. So here's what I mean. When working on a computer vision problem, part of my workflow is now repeatedly try to find examples where the label is either ambiguous or inconsistent, like the examples I showed, right? Number of bounding boxes, the label, then make a decision on how the images should be labeled. And I found that any decision is better than no decision. So just make a decision. Usually any decision is better than no decision. And then document that decision in your labeling instructions. And For a lot of my work at Landing AI, we found that the labeling instructions is that single source of truth that is the definition of what is the label y is a function of x, and label instructions should be labeled with examples of the concept. So show some examples of stretch pills, examples of borderline cases and near misses, and any of the confusing examples. And this document, when created properly, significantly increases label quality. Tip 4, toss out bad examples. More data is not always better. If I give you these 6 examples and ask you to train the learning algorithm to detect defects on pills, I don't know. It's like, yeah, there's a lot of stuff going on here. But if you were to spot that 3 of these images are actually poorly focused and have poor contrast and just toss those out, then even though with half the training set, with just the remaining 3 training examples, this is really clear now. It's much clearer what is the defect you're looking for. So I find that in machine learning, a lot of teams are used to being given a data set and trying to just work on the data set. And I know it feels like almost sacrilege sometimes to say, oh, let's throw some examples away. But that actually often improves the performance of your learning algorithm. Or go back to the camera operator and politely request that they refocus the cameras or change the contrast. And then tip 5, this turns out to be really critical, which is when you're given a data set, there's so many things you can work on. I think what Anima Anand-Kumar talked about some really cool data augmentation techniques. So we could pick a category and use data augmentation, or we could clean up some labels, or I don't know, refocus camera. There's just so much one could be working on. So I found that trying to improve data in a generic way is just too vague. So my typical workflow is now to repeatedly use error analysis to decide what part of the learning algorithm's performance is unacceptable or which you wish to improve. And if, for example, you decide that the performance is not good enough yet on scratches, then that allows you to focus attention on the subset of images with scratches. And this actually takes us to the workflow at the start of clarifying the labeling instructions of what is a scratch and what is not, and improving label consistency. So one of the still maybe less in this audience, but one of the common misconceptions of data-centric AI is that data-centric is about data pre-processing. I actually, don't love that term because I think that the iterative workflow of developing a machine learning system should involve engineering the data over and over. And so that many of you know that building a machine learning system is an iterative process. We train a model, then carry out error analysis to decide on the next step. And then when you decide you want to improve the system, one of the most powerful tools you can use is to engineer the data to fix whatever problems error analysis has shown up. And then you keep on training the model and iterating. So I think of entering the data not as a pre-processing step, but as a core part of the iterative process of machine learning model development. And so, how do you improve the data? Well, these are some things we kind of touched on. You can ask multiple labelers to measure consistency if you suspect why the label Y is inconsistent, or improve the label definitions and then relabel more consistently. So these are some tactics to improve the labels Y. Again, these are slightly more applicable to structured data, but there are other variations as well. Unstructured data, other variations as well to structured data. Or you can toss out noisy examples that improve the quality input Y, X, such as refocus the camera. Or if you find that your algorithm is doing poorly on one slice of the data, then data augmentation can be very valuable for that. So just to summarize, and just a couple more slides to wrap up. I think that improving the data, improving the data is not a pre-processing step that you do only once. It's part of the iterative process of model development. And I only spoke today about model development. I know that Sharon spoke earlier as well about data drift, concept drift, and how to detect that. But when you see data drift or concept drift, when something in the data tested distribution changes, I find that data-centric tools, closing the loop, taking the production data, spotting the concept of data drift, relabeling it, using that to monitor and maintain the system even post-deployment is an important part of the full cycle of a machine learning project. Listed the tips down below. I hope that if any of you are working on machine learning projects, that you could use these ideas right away. And in the case of computer vision, right? Landing AI has been building tools to support implementing these in a very efficient way as well. I want to mention as well, when I talk to people about data centric AI, I often get deja vu about some of the conversations that I and some of my friends had about a decade ago, or maybe 10, 12, 15 years ago, when we're trying to convince people to join deep learning, to shift the world to deep learning. I think the most important shift that the AI world went through in the last decade was the shift to deep learning. And I think the most important shift the AI world needs to go through in this decade will be a shift to data centric AI. So many years ago, maybe I'm doing this too long. I and my friends were organizing various workshops to try to gather, the nascent community to drive forward the movement on deep learning. And these days, I'm also involved in organizing, Neural's workshop, which we held December 14th, to try to coalesce, leaders in data-centric AI to try to move that forward as well. And I was actually very happy when Chris Ray accepted, our invitation to speak. So Chris always gives great talks. You should come to the Neural's workshop to his talk. Hopefully other great talks in addition to his as well. And I think, both, and I think, in addition to coming to the Neural's workshop, would love to hear any questions, comments you have, and please keep in touch. Social media, or I also write a weekly newsletter in The Batch, thebatch.ai, where I often try to share, the latest observations or the latest kind of state-of-the-art techniques to try to keep sharing ideas about data-centric AI. So that's it for my presentation. Thank you very much. We'd love to take questions or Q&A.
Thank you so much, Andrew. I can say I speak for the audience, but that left us wanting more. And also, I really admire the ability, to take learnings from the real world and then also just summarizing that into like actionable tips. I think we saw that also in your like machine learning yearning handbook that a lot of people have read over the years, just very actionable tips on how to improve performance. So great to see that here as well. We have a lot of we have a lot of questions popping up in the audience. So let me just walk through those. Roshni asks, if we toss out noisy examples from the training set, how will the model learn how to handle such examples in the wild?
Yeah, so it turns out, let's see. Actually, let me tell you a story. Uh, I think that a lot of us in AI, how to put it? Yes, so it really depends. If you expect to see a lot of those examples in a while, then maybe you need enough examples to have the learning algorithm learn to handle it. But sometimes you just have slightly weird, slightly non-representative examples. And when you have a small data set, if you have 50 examples and 3 of them are weird, that's a very large percentage. That's over 5% of the data set. And you actually do better tossing it out. If you have a bazillion examples, then maybe it's fine. Shove it out and let the learning algorithm sort it out. I find that when you're a consumer internet company with a billion users and does a bazillion training examples, bazillion is not a technical term, it's fine. But for almost all other industries where you have fewer than a billion users and does fewer than a bazillion examples, often data quality is the critical difference between whether or not you can get the application to work with the 50 or 70 or 100 or 200 examples, which will be all the data that exists in the world.
That makes sense. I recall when working with like defect detection, if it's any good of a manufacturing company, they don't have that many defective samples. So especially in the domains that you talked about, it's really important to feed in clean data there.
In fact, one of the things I'm excited about, I think, because of my leaving Google Brain, running AI for Baidu, I've sort of participated in the AI transformation of some consumer software internet companies, and I think that the hype on AI, is that we'll transform the world or something, which I think we will, but candidly, outside consumer software internet companies like the Google, Baidu, Facebook, Microsoft, and so on, if you look at AI deployments, candidly, I'm not seeing that much of it yet. Right? Financial service kind of getting there, but you've got a hospital, healthcare company, manufacturing company, agriculture company. Candidly, there are not that many applications of AI. I think one of the problems is the data set sizes are much smaller. And so part of the key, the recipe to unlocking, taking learning algorithms to all of these other industries will be tools that lets us build and deploy systems with smaller data sets, and data-centric tools, I think, will be a key part of that.
Makes sense. Yeah, excited to see this new wave of data-centric AI movement and having it unlock, value for the enterprise in addition to the consumer companies, as you've seen. Great. Next question we have from Roberto. Most data teams are afraid of going back and forth to touch a massive data set again. Will a data-centric AI approach allow data teams to iterate on vast data sets?
Yeah, I think it depends a lot on the nature of the data. So I think that uh, to me, a lot of it is about when you have a very large data set, you don't want maybe the data scientists to be relabeling, 10 million examples manually. Um, I think that for problems like that, you may end up having to rely more on automation to detect the problems or maybe fix other problems, or set up processes to have annotators to then gather to then relabel a large set of data. I think the tools and processes does change when you're in a large, very large, handling millions of examples scenario.
Makes sense. Just the scale is different, but sort of similar techniques maybe weed out noisy labels from smaller as well as larger data sets.
Oh, there is one other thing I want to say. I don't think I have all the answers, just to be completely clear. And just let's be candid. The way I think about it is about 10 years ago, a lot of people, including me, underestimated the amount of innovation and the thousands of, I don't know how tens of thousands of research papers that would be needed to take deep learning up to the current level of maturity. So I would predict that over the next decade, we may need, like an equally large body of research to flesh out all the labeling tools, data analysis, error analysis tools, how to do agreement-based labeling, consensus labeling, all of these things in order to flesh out a suite of ideas and tools and principles to engineer the data, just like in the last decade we did for the code.
Makes sense. And I think it's really exciting for both of our organizations to be at sort of the forefront of, data-centric AI movement and exploring approaches there. So that's been really exciting. Another question from Roshni. How can we practice data-centric AI application development when we don't have access to the annotators or the data generating infrastructure, like focusing on the camera? And I think this plays into, medical approaches we did where, doctor time is super expensive. So when you don't have access to multiple labelers, what are some alternative things one can do?
Yeah, and sometimes it's tough, right? Actually, I do want to say one thing. I feel like, all right, this is just story manufacturing with some details change. But once in a manufacturing context, someone was using a camera to inspect certain parts, and because the camera was not secured well, it just kept on falling. It just kept on slipping downward. And so, what the machine learning team did, they trained the system, and it worked fine, and then the camera slipped, right, just because of gravity. So the focus changed. So the performance degraded. Machine learning team said, "Oh, data drift. I got to get more data and train it." So they did. It worked. Camera slip. They said, "Oh, data drift. Get more data drift." The camera slip. And then until eventually a more senior guy said, "No, why don't you stop training the model? Just go and tighten the screw on the camera so it stops slipping." I find that robotics researchers are more used to designing the camera system, but I find that the way that AI has grown out, sometimes you don't have control. Is it this image off the internet? You can't change it or whatever. Sometimes it is what it is. But I find that some teams do have you could pay more attention to when you have power to change the lighting or the imaging system. But it's true. So if you have input to X, you can change that. Sometimes data augmentation lets you change X, and even if you don't have Y, and even if X is fixed, sometimes you can still change the labels Y. But sometimes it is true. Data off the internet, giant data set. Sometimes it's not going to be easy.
That is definitely a funny and entertaining story about just screwing on the camera. I remember when I used to work at Landing, like back in the day, it was like if the belt changes or lighting changes, it's like, how do you deal with that? And some of the earlier talks today talking about, just detecting that something has changed or out of distribution or things like that is really key to some of those problems that show up later. So that's exciting. Great. We have a question from John. He says, what's the trade-off between cleaning labels versus gathering more data, assuming you have a good held out test set?
Yeah, thank you, John. So let's see. It depends a lot on the application. I'm focusing a lot of my time on I find that for smallish data sets, mid-sized data sets, modern neural networks are basically a low bias but potentially high variance machine. So uh, if you have like 10,000 examples or fewer for a computer vision problem, a modern neural network of reasonable size is just a low bias thing. And so you're fighting variance all the time, hardly ever fighting bias. And I therefore tend to frankly spend less and less time on a good hyperparameter search is important, so do a robust hyperparameter search, but so long as you do that, for a lot of applications the model is basically a solved problem. Your mileage may vary. This is less true for really massive data sets. And then I tend to use an iterative workflow. Artie mentioned machine learning yearning. That's a kind of a free online book I wrote a couple of years ago. mlyearning.org, I think is the domain name, machine learning yearning, that talks about just some of the practices of error analysis as well, to focus, to help you systematically make the decision of, do you collect more data, do you use data augmentation, what exactly is the most fruitful next step.
Sense. Thank you, Andrew. Moving on to the next question. We're seeing a lot about like annotators being difficult, but I think you addressed a lot of those questions already. So a little different question. Could you talk a little about machine learning on structured data and any specific tips for structured data? So recent surveys do suggest that structured data still remains the main or even majority data modality in the enterprise. So how would you suggest these tips sort of apply there?
Yep, totally agree. Yeah, one of the double-edged sword, it is true. Majority of the world's of enterprise data is structured, but it's actually much more heterogeneous. Unstructured data, like a PNG file is a PNG file is a PNG file. So actually, unstructured data, images and audio, is actually more universal. But most data is structured, but it tends to be much more heterogeneous. I think that just on average, right, structured data harder maybe to rely on human labels. Depending on the application, your mileage may vary, and also when I work on structured data problems, I end up more often entering features rather than creating brand new examples. So data augmentation, you synthesize new examples maybe, but harder to do that on average for structured data. And we instead do focus on error analysis and then often engineer examples. For structured data, there's actually one thing that I know the panel, what Dario, Skip, and Charles talked about, which is bias. There's one other thing people often don't appreciate about data-centric AI, which is allows you to engineer one slice of the data at a time, which is why if you find that your system is biased against one demographic, it's actually a very powerful tool for building responsible AI, because how else can you engineer the performance on one subset or one slice of the data? So that's actually one very powerful thing I've seen a lot for structured data, a little bit unstructured data as well.
Amazing. Thank you so much, Andrew. We have a bunch of other questions in the chat. If you could just take the time to answer those in the chat after you're off stage, we'd really appreciate it. But thank you so much for taking the time to be here with us today, for your amazing presentation and for answering these questions.
No, thanks, Artie. Thanks everyone for joining us here today. It's good to be here with you. Thanks for all the questions.